Welcome to Module 4, The Nature of Seawater. In Module 4, we'll take a look at what is water. We'll look at the physical properties of water, both freshwater and seawater. We'll talk about water and the climate and water chemistry. What makes up seawater? What are the components that we find in seawater? The ocean is part of the global water cycle. You can think of it as a storage facility for water. So there are many different ways in which water can enter the ocean and which water can leave the ocean. Some of the ways that water enters the ocean is through surface runoff, through precipitation in the form of rain or snow, through groundwater seeping into the ocean, or from rivers carrying water into the ocean. Water can leave the ocean through such processes as evaporation, transpiration, and even through subduction. Water will be included in the subducting plate and make its way deep down into the Earth's interior. Once again, how much water is in this storage facility? We're looking at 1.37 billion cubic kilometers of water. Remember that 1 cubic meter of water is equivalent to 28 showers if you have a short sort of average shower of about 5 minutes, 111 toilet flushes. It's a lot of water no matter how you look at it. Over 97% of all water on or near the Earth's surface is contained in the ocean. So that means that over 97.5% of all water on the planet is salt water. And you look in this little jar here, the blue represents all the salt water present in the planet. The sort of the more oily looking clear layer represents all the fresh water. So most of the water on this planet, remember the planet, 71% of the planet is covered by the world's ocean, consists of salt water. So what is water? Well, the ancient Greeks, if you sort of go back into history, thought that everything on the planet was composed of 4 primary substances: earth, air, fire, and water. And for the longest time, this was believed to be correct, that water could not be divided any further. 100 years later, Aristotle said, yep, this is right. And other scientists of the time said, yep, only these 4 substances and everything on the planet, everything on the earth is made up of them. We can't divide them into any smaller components. And this ideal persisted for a very long time. It wasn't until the 1700s, almost 2,000 years later, that the Greeks and Aristotle and other scientists were proven wrong. How would you do this? You would do this by dividing one of the 4 primary substances, divide either fire, water, air, or earth, I believe. So this was done by Antoine Laurent Lavoisier and Marie-Anne Pallas Lavoisier in 1783. They can both be considered the discoverers of water, although we don't hear a lot about Marie-Anne. And what they did is they carried out a very elegant experiment that proved that water could be subdivided into other smaller particles. What they did is they set up an experiment in which, in this glass chamber, they pumped in 2 gases. They pumped in hydrogen gas and oxygen gas. And then they placed an electrical spark through it. What happened following the combustion of the 2 gases is that we saw condensation of droplets of liquid water within this particular container right here. So what this meant was that water had to be a product, or had to be some of these 2 gases. So in the 1700s then, we proved that water was a combination of hydrogen and oxygen. Water, in fact, could be subdivided into a smaller particle, a smaller molecule. So what we know now is that water is not an element, but it is made up of 2 elements. It's made up of hydrogen and oxygen. Water is known by its chemical formula H2O. This means that for every 2 hydrogen atoms, there has to be 1 oxygen atom. And this will never change. Water, as we know it, always will have that formula H2O, 2 hydrogens for 1 oxygen. So water, therefore, is a molecule. It's a group of atoms, hydrogen and oxygen, and they're held together by chemical bonds. In this case here, the chemical bond that is holding the 2 or the 3 atoms together is known as a covalent bond. This type of covalent bond means that the atoms are sharing electrons. Some atoms that we see, or some type of bonds that we see, is there's an exchange of electrons. In this case here, the atoms are being shared. And that's because if we look at the structure, for example, of a hydrogen or even an oxygen atom, we'll see that there's a central nucleus, and surrounding the nucleus are a series of shells. It's within these shells that electrons are distributed, and electrons orbit around the nucleus, which is made up of a proton and a neutron. In the shell closest to the neutron, we can contain 2 electrons. In the second shell second out from the nucleus, we can contain 6 electrons. What happens in order to distribute and have sort of an equal balanced electrical charge, that the positive protons equal the negative electrons, what we see is that by sharing electrons, the water molecule achieves this balanced charge. What happens is the outer shell of the oxygen atom, oxygen atom, wants to have 8 electrons in it. I think I said 6 before, but it should be 8. It only has 6, so basically it borrows, there we go, an extra electron or 2 from the hydrogen atoms. So within a water molecule, we see sharing of electrons between the hydrogen and the oxygen atoms. And once again, we see this here. The green dots on that circle represent the hydrogen, the electrons in the hydrogen. There's only one electron in each cell that wants to have 2 electrons on it. The outer shell of the oxygen has 6 electrons and wants to have 8. So by sharing those 2 electrons of the hydrogen, the 2 different hydrogen atoms, everyone is happy. So if you look at a water molecule, the 2 hydrogens of the oxygen, we'll see that it actually has a bent shape. The hydrogens are sort of attached, in this case here, let's say sort of the bottom lower portion of the oxygen, and the angle between the 2 hydrogen atoms is 105 degrees. And part of this is because oxygen as an atom is much bigger than the hydrogen. It's about 2 times the size of a hydrogen atom. So you get this sort of abnormal or this bent shape configuration to the water molecule. And this bent shape configuration of the water molecule is responsible for some very unique properties that water has that other fluids do not have. So what does the presence of this bent water molecule mean? The fact that the water molecule sort of has this bent configuration. Well, what it means is that due to the shape of the water molecule, due to the fact that it has this bend to it, due to the fact that there's a huge discrepancy between the size of the hydrogen atoms and the size of the oxygen atoms, is we see that even though the electrons are shared, they aren't shared equally. So because the oxygen atom is larger, it tends to pull more on the shared electrons. And what ends up is that there's more of a negative charge on the end of the oxygen part of the molecule, and there's more of a positive charge, a partial positive charge, on the ends of the 2 hydrogen atoms of the molecule. So once again, because oxygen is larger, it's kind of a bully. It attracts the negative or the negatively charged electrons towards it, so it has more of a negative charge. The hydrogen atoms have more of a positive charge. So now we have a molecule with a positive end and a negative end. It's sort of electrically asymmetrical. What happens then is we find that it's much easier to attract particles that also have a distinctive negative and positive end. In fact, it's much easier to attract other water molecules. So what you see happening is these water molecules that are covalently bonded molecules of hydrogen and oxygen will now start to bond to other water molecules, and they'll form something called a hydrogen bond. It's like the opposites attract. The positive side of the hydrogen ion, or the hydrogen part of the molecule, will be attracted to the negative part of the oxygen end of the other water molecule. And by this way, we get a whole bunch of molecules joining together, bonding together as a result of hydrogen bonds. Hydrogen bonds are the result of electrostatic forces, sort of that positive and negative attraction. And they usually are weaker bonds than we might see, weaker than the covalent bonds. So the hydrogen bonds that form between molecules are relatively weak. And this is one of the reasons why it's fairly easy with water to travel from or to transition from a solid phase to a liquid phase to a gaseous phase. Because what you need to do is you need to break those hydrogen bonds. What we see in a solid phase is that everything is bound together by hydrogen bonds. In a liquid phase, some of the molecules are on their own, some are bonded through hydrogen bonds to other molecules, and in a gaseous phase, there are no hydrogen bonds. Every molecule is like for itself, is on its own. So because these bonds between water molecules are relatively weak, it's almost like a loose attraction, As I said, it's very easy to break these hydrogen bonds. It's one of the reasons why we can dive into water, why we can walk through steam, why it's fairly easy to move through water. We can stick our hand through flowing water. It's because it's very easy to break these weaker hydrogen bonds. The presence of these hydrogen bonds, remember, once again, the hydrogen bonds occur because of the bent nature of the water molecule, which leads the water molecule to have a positive and negatively charged ends, can also be responsible for a number of other properties that we see. And one of these properties is how sticky the water is. And we can talk about the stickiness of water in regards to either cohesion, the fact that one water molecule will be attracted to other water molecules, or adhesion. Water will stick or is attracted to other substances. So cohesion, the ability of individual water molecules to stick to one another. This is what creates surface tension in water, which once again is fairly easy to break, but for animals such as these little water bugs here, allows them to move and travel across the surface of the water. Adhesion, well, if you watch raindrops dripping down a window while it's raining, you'll see that sort of one raindrop will move down the window, then it'll stick and clump together to another raindrop. That's an example of both adhesion and cohesion. The tendency of water to stick to other materials. You see this here with these raindrops on this blade of grass. This also means the fact that we have a positive and negative end to the water molecule, that water can dissolve more substances than almost any other liquid on the planet. So water is known as a universal solvent. One of the reasons why it's known as a universal solvent is because, as I said, it is something that is called a polar molecule. A polar molecule means that we have a positive end and a negative end. And I know this isn't a term I've used yet, but we will start using it more and more. So a water molecule is polar. It has that positively charged end where the hydrogens sit, and that negatively charged end where the much larger oxygen atom sits. Once again, opposites attract. So you put a substance in the water, and it's going to very easily dissolve that substance, depending on what the substance is. So one example of how material dissolves in water is looking at salt. And salt has the chemical formula of NaCl, sodium chloride. Sodium, as we find out in this particular configuration, will have a positive charge. Chloride, Cl, will have a slightly negative charge. These are known as ions, atoms that have an unbalanced charge. They either have an extra atom or have lost an electron. If I said extra atom, I meant they gain an electron or they lose an electron. Once again, they're held together by electrostatic attraction. So if you take that salt, and there's some lovely salt crystals here in this image here, and we place it within water, that electrostatic reaction or attraction between the sodium and the chloride is reduced. It's reduced by a factor of about 80 times. And what happens now is sort of the positive end of the sodium, or the positively charged sodium, is attracted to the negative end of the oxygen part of the water molecule. The negatively charged chloride is attracted to the positively charged hydrogen end of the water molecule, and you basically split or break apart the salt crystals within the water. This slide illustrates sort of what I've been talking about in the previous slide. So here we have a little container of water. You put some salt in, and basically because of this attraction between the positive and the negative charged ends of the chloride and sodium ions, as well as the positive and negative charged ends of the water molecule, you basically pull that salt apart grain by grain by grain. Eventually the salt disappears, and we can say that it is in solution, and water, once again, is a universal solvent. It's a solvent. It's what the salt has dissolved into. What are some other physical properties of water? We'll take a few minutes and look at those. Water can exist on the earth as all three phases. And if you start thinking about it, there's not a lot of other substances that can exist as all three phases on the earth at the same time. So you can see water existing as a solid. Here we see it as snow on the trees. As liquid, here's that little bit of liquid surrounding that sort of that steam vent, and then as a gas. And why is it? Well, it has a lot to do with how water changes from one state to another, and the energies that are required to cause water to change from one state to another. So one of the reasons, if we look at chemical substances. So water freezes or melts at 0 degrees Celsius. Water boils or condenses, goes from a steam to water to liquid at 100 degrees Celsius. And the reason why, once again, is because water is a polar molecule. And we'll explore these reasons why in a couple of slides from now. So for water to change from one state to another, to go from a solid to liquid to gas, or vice versa, from a gas to a solid to a liquid, what we need to do is we need to break bonds between molecules. And when you break bonds or create bonds, what you're doing is you're using energy, and this is using a type of energy known as kinetic energy. Kinetic energy is energy that an object has because of its motion. So here we have a roller coaster. The cars are sitting right at the top of a slope. As it moves down that slope, it's going to have kinetic energy. The faster an object moves, the more kinetic energy it has. And what we'll find out is that heat is proportional to the average kinetic energy of molecules in a body. Water will exist in a state of either gas or liquid or a solid, depending on how much heat is added and what the kinetic energy is. When discussing kinetic energy, we need to mention the differences between heat and temperature. So heat is the amount of energy that is transferred from one body to another due to a difference in temperature. So the air around you might be cold, you might be warm. There's going to be a transfer of heat from you to the air. It's proportional to the average kinetic energy of the molecules in a body, and we can measure heat in either calories or joules. Temperature, on the other hand, is the direct measurement of the average kinetic energy of the molecules that make up a substance. So the greater the temperature, the greater the kinetic energy. How quickly are these molecules that are making up that substance moving? And temperature can be measured in degrees Celsius.